Okay, good afternoon, everyone. Welcome back to this week's edition of the Brazilian Algebraic Geometry Seminar. It's my pleasure today to introduce Pietro Speziali. Now, just from the past year, professor here at the IMEC in Campinas. And today he'll tell us about symmetries of an algebraic curve, the challenges of the positive characteristic. Pietro, please go ahead.
Thank you very much, Marcos. It is a pleasure to be here. I want to thank Marcos and the other organizers for giving me the opportunity to give this talk, for the invitation. It's really nice to be, well, here and everywhere. Yeah. So today's talk, it will be somewhat general. I mean, I thought since I know that the problem of automorphism groups of algebraic curves in the case of positive characteristic might not so well be well known to the general public. So I thought to make some sort of general, gentle introduction to the kind of techniques and problems that we have, why it is interesting, give some motivation, and then I will take the opportunity to talk about some more recent or less recent work of mine related to this, which is the mathematical problem which interests me the most at the moment. So a little bit of an introduction. Who knows me know that I like to start with some motivating quotes. This excerpt is taken from the book Algebraic Curves Over a Finite Field, which in our small world of curves over finite fields, or in positive characteristics, we nicknamed the Bible. So the book is wrote by Professor Hirschfeld, Professor Gabor Korczmarus, my former PhD advisor, and Fernando Torres, our dearest friend, which I would like to take a moment to remember his legacy. So, what is a symmetry? What do we mean by a symmetry? In modern terms, these are automorphism groups of algebraic curves. When you have a geometrical object, in general, you expect it to have no symmetry. I mean, no automorphism. But when you do have some curves, in this case, which happen to have many automorphisms, then usually you have a rich geometry. So the properties are interesting. So in some way, we are interested in the nicest exceptions that we can find. And this excerpt is taken from chapter 11, which is devoted to algebraic curves, to the automorphism groups of algebraic curves. And a reading that I strongly recommend to anybody who is willing to start to learn about it. And the postscriptum is mine. So this is especially appropriate for algebraic curves, and even more so in positive characteristic, because positive characteristic is where funny things happen. Let's take a look with some examples. So, as I mentioned, all this story actually starts in characteristic 0 with proof of the classical Hurwitz bound. So when you have the introduction of Riemann surfaces, then it took some 40 years to understand that actually when you have a curve or a Riemann surface of genus greater than or equal to bigger than or equal to 2, then you're dealing with finite groups of automorphisms. And Hurwitz proved the classical Hurwitz bounds, which tells you, well, how is the size of the automorphism group related to the genus of your Riemann surface? Well, it's at most linear. So it's a function which is upper bounded by 84g minus 1. So of course, whenever you have a bound, you may ask yourself, is this bound sharp? Do I have examples? Well, a Hurwitz curve is a curve attaining the Hurwitz bound. In this case, we know a lot about the automorphism groups. So it's a group which is generated by two elements, one of order 2, one of order 3, and then their product as order 7. Actually, you do have the signature. So the quotient curve has genus 0. Then you have an orbit which is stabilized by the evolution, an orbit which is stabilized by an element of order 3, and an orbit which is stabilized by an element of order 7. And you have an infinite sequence of such curves. Actually, you don't have Hurwitz curves for any genus. You have, for instance, genus 3, then when you have the famous Klein quartic, genus 7, you have the Fricke-McBeat curve. Genus 14, you have 3 non-isomorphic curves, which are somewhat elusive. And just a side note, here you have a very nice play model, which is defined over Q. Here as well. From here on, for what I know, the minimal field of definitions of an algebraic model of these curves is at least a quadratic field. So then, why don't we go to the smallest examples, the Klein quartic, and see what we can say if there is something different happening in positive characteristic. So this is the very nice equation of the Klein quartic: x to the cube y plus y to the cube z plus z cube x equals 0. So over Z, the automorphism group, over C, the automorphism group is PSL to 7. So we have 168 automorphisms, and the Hurwitz bound is attained. Well, why I don't consider this, for example, over an algebraically closed field of order of characteristic 3? The funny thing is actually you can restrict yourself to F9, but this is another matter. So you start thinking, well, what is always true? Curve of genus 3, if it's non-hyperlytic, then it has a plane model which is given by a non-singular quartic. Non-singular curves degree more bigger than 3, then you have Segre's theorem, which tells you that the automorphism group is linear. That is to say, a finite subgroup of PGL 3K. So we start to think, well, in this case, I might have more subgroups. And this is actually what's happening. So in this case, you have that this curve admits PSU 33 as automorphism group, which has this size 6,448, which is a lot bigger than 16 genus to the 4th. I know that this might sound a bit arbitrary, but keep in mind this bound because it will play a role later. So we start thinking, okay, well, the characteristic is 3. So I can expect that the seal of 3 subgroups might be bigger, which is actually what happens. Here you have seal of order 3. When you consider in this case, then S3 has size, seal of 3 subgroups, has size 27. But actually what is worth noticing, which is another thing that we could not expect, and that we also have extra automorphisms in the seal of 2 subgroups. Because this is 32. A lot more than here. Because here we had a group of order 8. So we have a further funny thing happening here. Because what's at the core of this? Over an algebraically closed field of characteristic 3, the Klein quartic is actually isomorphic to the Fermat quartic. And from here, we inherit these extra automorphisms in the seal of 2 subgroups. So you see, there are a lot of strange things going on here. And so I hope that until the end of this talk, I will give you some sort of intuition of why this happens. So just to mention a little bit the historical background behind, because what happens here is the following. So the first studies of automorphism groups of Riemann surfaces is end of 19th century. If you see the flourishing of studies of automorphism groups of, well, algebraic function fields of transcendency degree 1 function fields, actually over fields of positive characteristic, you have to wait the 30s. Actually, the result that says that if you have a curve defined an algebraically closed field of characteristic, at least 2, well, first characteristic, and of genus greater than or equal to 2, it is a finite group, is due to this Schmidt, and is around 1930. So why am I stressing so much the fact that they were studying transcendency degree 1 function fields? Well, when you're not in the world, we are not anymore in the complex world. You don't even have the intuition of the genus of the topological genus, right? You don't have topology to help you. So, for instance, if you the first time it was introduced, the concept of the genus was through Riemann's theorem. So prelude to Riemann-Hock. So it's in this sense, when you're studying positive characteristic, it's natural that the main tool of study of an algebraic curve, even though if you're dealing with the geometry, is its function field. So this also explains some weird stuff about our area, because since we look at curves essentially from a birational point of view. So what is birational? Two curves are birational equivalent if they have the same function field up to the same function field up to isomorphism. So we always say that we study non-singular curves, but we're not shy about using singular plane models, which will give the function field. So there is always this interplay between what to say when we say a point, we actually mean a place in the function field and everything. So this, and I have to mention the fact that, well, one of the main reasons of the more modern interest in the symmetries of algebraic curves is actually given by applications. So in the 80s, the world knew about Gopa's construction of linear codes arising from algebraic curves over finite fields. And actually, well, more recently, we now know that in some sort of weak sense, any linear code is algebraic geometric. So it's somehow induced by Gopa code from an algebraic curve. And actually, so so not any curve will give you good codes. So when do you have good codes? You have good codes when you have many points with respect to the genus. So for instance, the so-called maximal curves, and also many automorphisms over FQ when compared to G. The automorphisms actually are interesting from the point of view of the coding, because when you have a linear code, you want some features which sometimes are rather technical, but from the point of view of the application, if you don't have a fast decoding process of a code, it can be as good as you want, but it's not practical to use. Symmetries of the curve induce automorphisms of the linear code you construct from them, and then you have excel in decoding. So this is another motivation, so to speak, to study automorphism groups. So so just another example, practical, to see what I mean by an automorphism of the curve. So I told you that essentially we deal with the function fields of algebraic curves. So what is an automorphism of a curve? It's an automorphism of its function field. So here, this is it's a very simple yet wonderful curve. It's very beautiful. It's the so-called Artin-Mumford curve. This is short for Artin-Schreier-Mumford curve. So you see, we have this equation. We have a constant c, which in FP, which is non-zero in FP, and then you take this curve x to the p minus x. Of course, p is the characteristic of the field. Y to the p minus y equals c. So there are some maps which are automorphism of this curve that we can construct by hand. For instance, if you take this map tau a b, saying in x and y, x plus a, y plus b, where I, b are in FP, this preserves the equation, preserves the function field. This is an automorphism. Then you can flip, you can switch x and y, another automorphism. In the end, you have this cyclic group here of order p minus 1, given by multiplying d by x, x by a d with a non-zero d in FP, and y to d by d minus 1. So we have here cyclic group Cp, here, which commutes with another automorphism, with another cyclic group Cp. Then these two generate a dihedral group of order p minus 1. Then you can prove that this dihedral group normalizes Cp times Cp. So you have these many automorphisms. So the challenge is this the first question, is this the full automorphism group? Do we have extra automorphisms? And this is in general a very complicated question. The last thing I will show you how sometimes it's really hard to say this. But well, when p is bigger than 2, then this is all the automorphisms we got. So actually, this is the full automorphism group. The genus, well, this is a standard Artin-Schreier theory, is p minus 1 squared. So you see that actually, so we have p squared times 2p with the size of automorphism group. So actually, we have some genus to the 3 to the 2, roughly, automorphism group, automorphisms. And what's interesting here is that, so here we are above. This is another example of a curve which is not so above as the Klein quartile characteristic 3, but it's above the Hurwitz bound for p bigger, for b big enough. And actually, this curve answered a question posed by Mumford, because at the time around mid 70s, the only automorphism group, the only curves with too many automorphism groups had too many automorphisms had p rank 0. So at the opposite side of the spectrum, I will get to what it is the p rank in a few slides. We have the ordinary curves, which are ordinary in a moduli space sense. So nearly all curves are ordinary in this sense. Then, so Mumford asked, do we have ordinary curves beating the Hurwitz bound? And this was the first example. Another interesting thing, so sometimes, when you have a curve, you may ask yourself, well, which is the minimal set of birational invariants which are enough to characterize it? Well, in this case, the genus and automorphism groups completely characterize this Artin-Mumford curve. It's a pretty recent result by Artin and Hurwitz. So, okay, done with the introduction, let's fix some terminology. So I will always work on an algebraically closed field of characteristic p bigger than 0. X is a projective non-singular, absolutely irreducible curve over k. K of x will be its function field, and the automorphism group of a curve is, by definition, the automorphism group of its function field. Actually, I mean, I could define, since any curve has a canonical model, on hyperelliptic at the least, which lives in a projective space of dimension g-1, we could also say, well, you have the canonical model. The canonical model is non-singular. You can see the automorphism group also there. But for me, it's quicker to define it this way. So we have the set of places of k of x, and this set is in bijection with the points of x. So we have divisors, which are formal sums of places in k of x. The degree of a divisor is the sum of their weights, and actually we have a free abelian divisor group, which is, well, the group generated after this formal sum by all the divisors on x. So I told you enough that, well, I've been made clear enough that basically we'll work a lot with function fields. So let's get to the function field of a curve. If we have a curve, we have a function which is non-constant on x, then to this curve we can associate a divisor, which is its divisor, div f, which is, well, given by the zeros and the poles. So we have the zero divisor and the pole divisor of f. The interesting thing, one is the degree of this divisor is 0, and so to each function we can associate a divisor. But of course, as you all may know, given a divisor of x, we can associate well, not a function, but of spaces of function, the Riemann rock space, the function whose pole divisor is bigger than or equal to minus g. I will also need the concept of a local parameter, so function at a point, what a place, which is a function whose valuation is 1. In characteristics p, we also need the concept of the separating variables, which is, well, it's any function which is not a p power. And these are really useful because each function can be decomposed, as you can see, as u0p, but u1 to the p x plus blah, 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 u to the p minus 1, x to the p minus 1. And this holds for any function. This is actually pretty useful when you want to look at the action of the Cartier operator in the space of all orbit figure differentials. So let's get a look of the genus of what is the genus of a curve and how it is relevant. Of course, it is the prince of birational invariance. As I told you, it's related to, well, you have the Riemann-Roch theorem, so we have the dimension of L of G of the Riemann-Roch spaces. The Riemann hypothesis over finite fields holds true. So we have that the zeta function of a curve is this rational function whose numerator is actually a polynomial of degree 2g. as a consequence of this, we have the famous Hasse-Weil bound on the number of FQ rational points of a curve. So you see, this is x of FQ is the number of FQ rational points of a curve X. And now it's upper bounded by Q plus 1 plus 2G root square root of Q, and it's lower bounded by Q plus 1 minus 2G root Q. And of course, as it happens in characteristic 0, then we have a lot of bounds on the sides of the automorphism group depending on the genus. Of course, in general, it might be hard to compute the genus, but one of the main tools we have is Hurwitz's theorem. So if we have a non-constant rational map between two curves x and y of degree n, then you have this closed formula relating the genus of x, the genus of y, the degree of the covering, and this mysterious degree of the different. So which is well, in characteristic 0 is not so mysterious, but in positive characteristic might be hard, but you may not have separable maps and anything. But take a point on a curve, and take a subgroup of the automorphism group of X. We consider the stabilizer of this point P as P. So as you all know, in characteristic 0, the stabilizer is a cyclic group. But when the characteristic is positive, this may be no longer true. Actually, we have a normal P group normalized by a cyclic group whose size is not divided by the characteristic. So of course, we may have all these cyclic groups, but in general, this is not the case. Also, we have to take care of the so-called ith ramification group of X at P. What is this? So we have automorphisms fixing these points such that the valuation at P of the image of a uniformizer minus this of the uniformizer is bigger than or equal to I plus 1. So these groups might be non-trivial and they give a contribution to the different. So since an automorphism induces a non-constant rational map, because, well, we can think geometrically as follows. We have an automorphisms, then a finite group will act on the points, these are orbits, then you identify points which are in the same orbits, so orbits might be long or short, and then this gives you a curve, an underlying curve, which is called the quotient curve. And so what about the Hurwitz genus formula in this case? Well, it reads this way. So we have, again, 2g minus 2, the degree is the size of the automorphism group. Here we have g bar, which is the genus of the quotient curve, and then this huge sum. Well, this can be huge. And actually, if you take the size of the short orbs of X, so of the points, who was not one point stabilizer is non-trivial, then you always have this inequality. You may recognize this as the usual Hurwitz formula, Riemann-Hurwitz formula in characteristic 0. And if the GCD between the size of SP and P is 1 for all P in X, then this equality holds. So you recover what you have in characteristic 0. But in general, this might not work. And so you see why we may have more, than a linear function on the automorphism group. Because here we have the genus, here we have G bar, and here this sum grows a lot. So the constraints you have in characteristic 0 no longer will hold true. So you may ask yourself, well, in positive characteristic, I may have further invariance of the curves, which may help in studying, in understanding the behavior of the automorphism group of the curve. And maybe they behave better than the genus when related to P groups. Do we have such an such a guy? Well, we do have. It's the so-called P rank. So the P rank is a non-negative integer, which is upper bounded by the genus, and it's at least 0. Well, we have many equivalent definitions. My favorite one is the first one. So it's an invariant which counts the number of independent field extension, which are a ramified and elementary abelian of degree P of the function field of the curve. Or also, if you like if you prefer, if you have the p torsion groups of the points of the Jacobian of the curve, this is a group of cardinality p to the gamma. So, and well, in general, the generic case is gamma equal to G. That's why we call these ordinary curves. But we may have curves of P rank 0. And so we have this formula, which is the celebrated Doring-Shafarevich formula, which relates the P rank of two curves when one is a P to the K covering of the other. So we have a P subgroup of automorphisms of a curve X, and then we have gamma minus 1 is equal to P to the K, so the degree of the covering again, gamma bar minus 1, plus this guy, which is the contribution to the difference we would expect in characteristic 0. So we have the size of the short orbits. This is actually pretty useful to compute the P rank when you have P groups. The challenge is, what about the P rank when you don't have P subgroups? This leads to very, very complicated combinatorial problems. So now I would like to take a little pause to present some results and tools, some general results and tools. Also to summarize things that I have said and well, maybe, but have not fixed on the board. So if you, as I told you, we have a finite group. If the automorphism group of a curve of genus greater than or equal to 2, we have finite groups. So we can think on the inverse Galois problem. We do have this, but then this is solved. So every finite group is automorphism group of some curve. I will give a more precise statement later. If P does not divide the size of the automorphism group, we're done. Well, we have the Hurwitz bound. So pretty much anything that you know in characteristic 0 still works. With a small problem, you don't have topology, hence you don't have Fuchsian groups. So sometimes to prove the same result, you have to make some really cumbersome application of the Riemann-Hurwitz formula, which is about all you have. I told you that 16G to the fourth was not seemed arbitrary, but indeed it was not. So apart from an exception, which is the Hermitian curve, then you have at most 16G to the fourth automorphisms. Actually, we can be a little more precise than this. But then, and this last result here is sharper than here. So actually, if you have no P group fixing some point on the curve, then the Hurwitz bound holds. This is basically what we are saying. And we say the G is tame in this case. So when the GCD of the characteristic and the stabilizer of any point of the curve is 1. So tame group Hurwitz bound holds, and we are like in a characteristic 0-like case. So what are the tools we may use? So as I mentioned, we have no topological methods. And you may think, well, we will have Weierstrass points, but then the action of Weierstrass points may be difficult to deal with because we may have non-classical curves, meaning that in general, there are curves whose generic gap sequence is different from 1 to G. So sometimes you don't even know if your point is actually a Weierstrass point. So you're studying the action on an orbit, but you don't know much. So we use a lot of functional field theory, as I mentioned, Galois theory, the Hurwitz formula, and deeper results from finite group theory. So this is actually something pretty, well, now it's not new, but it's pretty recent in the area, because up to the early 2000s, no deep result of automorphism about finite group theory had been used in the automorphism group of algebraic curves. I will show you some examples of how this can make our life a lot easier. Also, I told you about the inverse Galois problem for curves. So if we have a finite group, there exist infinitely many non-isomorphic curves that admit this group as an automorphism. But there is a twist on this. When you have curves of even genus in characteristic bigger than 2, this is not true. Actually, this is true even in characteristic 0. And this happens, this is a beautiful result by Professor Korczmarek and Professor Giulietti, which relied by a simple application of the Riemann-Hurwitz formula to a seal of two subgroup of a automorphism group of a curve of even genus, which actually, if you just make the computations, you see that this group, it's either cyclic or has a cyclic group of index 2. But then from finite group theory, we know, okay, these groups have been classified. So I will show you later the sort of complete list of possibilities. So this gives a huge restriction. So in the even genus case, you have a lot more tools to work with. So now I've mentioned the P rank, which is the thing which is really new with respect to positive characteristic. So after the end of this interlude, I would like to show you how the P rank and the automorphism group relate. So this is a seminal work, a paper by Nakajima in 1987, which has sparked a lot of research up to this day, actually. So if we take a curve defined on an algebraically closed field of characteristic P, genus bigger than 2, and then we take a seal of P subgroup of the automorphism group, how is it related to the P rank? So, well, the seal of, if you have a curve whose P rank is bigger than 2, then a seal of subgroup is upper bounded by a linear function in the P rank. This constant Cp is P over P minus 2 when P is greater than or bigger. It's actually can be equal to 3, and C2 is 4. And there is a lot of research and of curves which are extremal. With this bound is sharp is obtained actually, and extremal Nakajima extremal curves are really interesting to begin with. The Artin-Mumford curve I showed you before is an example. If when the P rank is 1 and the characteristic is big enough, then you have that the seal of subgroup must be cyclic, and his size divides G minus 1. And it fixes no point, actually. P rank 1, characteristic 2, well, we always have a linear function. And then you get to the 0 P rank case, where you see that the size of an automorphism group actually is upper bounded by the maximum between the genus and this quadratic function on the genus. So you see further notice that how big automorphism group can be in characteristic P. And actually the Klein quarter in characteristic 3 has P rank 0 and is an example of an extremal curve with respect to this lesser bound. So of course, well, so we have seen here that maybe the case where I can expect to have more control is the case when the P rank is positive. And what about the case when it's equal to genus, which as I told you is the generic case? So Nakajima proved that when you have an ordinary curve, actually you can have at most 84 G squared minus G automorphisms. But this bound is, well, it should not be sharp. I will get to why in a moment. And then if you have a P subgroup which is bigger than 2P times P over P minus 2 times the genus, then you have the P rank 0. There is actually a lot of research on curves with big P seal of P subgroups when you can like lower this constant and see what you can do. Generally speaking, you either have an ordinary curve with many automorphisms of a curve with P rank 0. And there is a classical problem then which arises, which say, well, so all the curves with too many automorphisms I know have P rank 0. Is it possible to find a minimal function f of g such that the size of if the size of the automorphism group is bigger than f of g, then the P rank is 0? This is something around constant g to the g squared. But still, we don't know the minimal function, so it's still an open problem. But yes, but then I told you here that this bound should not be sharp. So let's see why. And but before we get there, let's look at the opposite side of the spectrum. As I told you, we have just one curve with more than 16 G to the 4th automorphisms, which is the Hermitian curve. Then there is Hen better these results in 1978, telling you how many curves has more than 8g to the cube automorphisms. So we have the Hermitian curve, the Suzuki curve in characteristic 2, and we have these two hyperelliptic curves in characteristic. This is called, or usually called rocket curves. One in characteristic 2, and the other one in characteristic one bigger than 2, one characteristic 2. And all these examples have 0 P rank. So this tells you why the problem above arose and how it arose. So you may ask, well, do I have some tools to deal with this case? What happens here is the following. The larger, if you are familiar with the classical proof of the Hurwitz bound, you know that the larger the automorphism group gets, the less options for the action of the group you have. So when it's big enough, you have just 3 orbits. So when you are above 84 G-1 automorphisms, what happens? So actually the action of the group is somewhat rigid. You may have 2 short orbits, which are both non-tame. Here it means that the 1 point stabilizer of a point in both orbits is has sides divided by p. Or you have 3 short orbits. One is non-tame, and the other 2 have involutions or stabilizers. And in this case, you have at most 24 g to the square automorphisms. You have a unique short orbit, which is non-tame, so you have at most 8 g cube automorphisms. And then the last case, which is the most difficult to deal with, 2 short orbits, and 1 short orbit is tame and the other is non-tame. So this actually, there is a recent paper which was in our archive about 2 weeks ago that tells you that, well, in this case, if I'm not very much mistaken, it should be less than 2,656 g squared. So here what we use a lot is this fact, because you can use permutation representation on these short orbits, and then, well, right. Just to mention, so the only proof I have seen of this result invokes the classification of 2 transitive automorphism permutation groups where the stabilizer of 2 points is cyclic. So, you know, again, deep group theory, which can be used. But then, so this is a further tool we use a lot. Sometimes it's hard to use, but well, it's something. So then I told you about something about the 0 P rank case. Then let's go to the opposite side of the spectrum, ordinary curves, which is, well, the generic case. So let me recall, I told you, Nakajima tells you that at most you have 84 g squared minus g automorphisms. This has been bettered in 2015. So by 6 g squared plus this constant times g3 to the 3/2. But even this bound is far from optimal. There is the unpublished result by Guralnik Ziv, which has been talked around since 2004, which tells you there exists a constant depending on the characteristics such that the size of the automorphism group is at most constant times g to 8/5. So this is actually sharp. So we do have an example here, which is called the Dixon-Guralnik-Ziv curve. And it's the only example we have. If I have to give you my 2 cents, I will tell you, and then it will be clear why, that the real bound for ordinary curves is constant g to the 3/2, and this is the only exception. So I expect some result akin to the 0 P rank case. Up to you have one bound, which is, say, something g to the 3/2, and then you just have an exception. Well, actually 2, but 1 is sporadic above. So why is this so? Well, for solvable groups, we know that the bound is sharper, is tighter. So it's g plus 1, 3 to the 3/2 times 34. This is a result by Kochmaros and Montanucci, and this is not characteristic. But so for the even genus case, we actually did something better. So because even genus, we have the structure with the possible structures of the group. So it's not easy, but if you take some time, you can actually prove that at most you have constants like genus to the 7/4 automorphisms. And so here in this was P odd. So we did also for solvable groups, the version in characteristic 2. And well, also we need the genus be even for technical reasons. But then again, the real bound for solvable group in this case is G to the 3/2. So and now we have some further examples of coordinary curves with non-solvable automorphism groups, which is genus to the 3/2. So I think that we're gathering enough evidence. I'm pretty convinced about this, but still have no proof, of course. So, and here what we used that if we just to show you how strict can be the given genus case. If you have an odd core free group, well, we could prove that in our case we had non-abelian simple minimal normal subgroups. The odd core of the group was trivial. Then one of these cases occurs. So you see that you have not many possibilities. I will show you the full possibilities of even genus a bit later. But then we have PSL to Q, P gamma to Q. So we have linear or semi-linear groups of small dimension, which is a blessing. And then, or we may have Alt7 or M11. So we get even to sporadic groups. So I will, this ends the part about the P rank. And in the last part of the talk, do I have some 10 minutes maybe, Marcos?
Yes, yes,
Yeah.
you do.
Thank you. So since I talked more about P rank, I wanted also to show you what we can do when you have no information on the P rank, because maybe you cannot compute it, or maybe you're working over many characteristics at the same time, so it may vary and it gives you little information. And so this last part is based on a joint work with Noether and Achille. So, and actually here this work was motivated by some study in characteristic 0. So you may ask yourself, well, we have finite groups. Okay, so their size will be divided by a finite number of prime numbers. Okay, do I have some sort of control over the size of the prime dividing the size of automorphism? So we gave this non-standard definition. If you have a prime number Q, a curve defined over K is a Q curve, if the automorphism group contains a cyclic group of order Q. We say tame, we have the tame case when it is same. So if Q is not a characteristic of the field, or you're working characteristic 0, otherwise we say wild, because that's the so-called case of wild ramification. So Homma in 1980 proved this, which is any characteristic version of classical result that you can find in Ricky Miranda's book or Farkas, that you have a prime number, there's an order automorphism group on a curve, then either this prime is at most G plus 1. Well, this Q equal to G minus 1 is cheating, but it might be, but it has to be equal to 3. And G is to G plus 1. So Homma proved actually proved it in the tame case, because again, you have no Fuchsian groups, and in the wild case. So when you have G plus 1, 2G plus 1 or G plus 1, you may hope to characterize this curve. And when you classify these curves, you may ask yourself, well, how's the automorphism group like? What does it look like? Homma also classified the 2G plus 1 curves. So basically, in the tame case, characteristic 0 or different 2G plus 1, you have these curves here, which are actually, well, what that essentially says that your automorphism group of order 2G plus 1 fixes 3 points, and the quotient curve is rational, so it's P1, the projected line. While in the wild case, you have this, which is a Hockett curve, so a hyperelliptic curve. So one of the first things we thought is, can we characterize the G plus 1 curve? And actually we did. Here you can see it's similar, but not that similar. So we have the thing for the tame case, we have basically this family, of curves. Here, what we are basically saying is that an automorphism group of order G plus 1 prime fixes 4 points, and the quotient curve, again, is rational. But when the characteristic is G plus 1, you may have hyperelliptic curves or this kind of trigonal curves. So, well, classification was just function field theory. So this part was, well, say easy. Then, well, this is classical as well. You have a huge family of curves because it depends on a lot of parameters here actually. So you may want to characterize the hyperelliptic ones within your family, this is classical again. So based on information automorphism group, first we gave an implicit characterization, meaning that, well, it must be, if it's hyperelliptic, it must be isomorphic to this guy you can see here. Y squared equal x to the G plus 1 minus a0, x to the G plus 1 minus a1. Concretely, this means that you have a lot of restrictions on your R, S, and T. So we gave, so if you have a tame G plus 1 curve, I give you the equation. If satisfies these constraints here, it's hyperelliptic. If not, it's not. So then, so once we settle this, because of course, if in the hyperelliptic case, you have the hyperelliptic involution, which is normal in the automorphism group, and the quotient is isomorphic to a finite subgroup of PGL to K. So you have a lot of information there. So the first thing we managed to prove here is the full automorphism group of a tame 2G plus 1 curve. So what happens here is the following. Generically, you have the 2G plus 1 group is normal in the automorphism group. So you have at most, you have either 2G plus 1 or 2G plus 1 or 3 times 2G plus 1 automorphisms. Unless the genus is power of the power is d to the h times d to h minus 1 over 2, where this is some prime, and x is actually your Hermitian curve. Because the thing is, we know that the Hermitian curve could be, in some cases, a 2G plus 1 curve. But then you may ask, okay, how did you manage to prove this? And well, this was highly non-trivial. So you see, sometimes you can see by hand some automorphisms, and then the real challenge is how do you prove that that's so or not? Because in some cases it was not. So I will just give the idea, as I told you, a cyclic group order 2G plus 1 fixes 3 points. This cyclic group is a seal of 2G plus 1 subgroup. So if you have the normalizer of this group, since you have 3 fixed points, then it must act on these 3 points. So the normalizer is a subgroup, well, normalizer quotient by C2G plus 1 is a subgroup of S3. We want to exclude the hyperelliptic case, so well, you don't want this guy to be divided by 2 because we can prove that in this case it was hyperelliptic. So another thing, this is a result I put here because I wanted to highlight it. I could have put in the beginning, but then it would be lost. So if you have an automorphism curve defined over a field of characteristic bigger than G plus 1, then the automorphism group is upper bounded by the Hurwitz bound, with just one exception, the Hockett curve, which is one of the exceptions we saw before. So this means that we could work on fields of small characteristic, and this helped us in some technical results. We also wondered what happened in the characteristic 0 case. Well, in characteristic 0, actually Seyama had already proved that you have, or just the automorphism you can construct by hand via the automorphism group of order 2G plus 1 by then the normalizer, unless you had, again, the Klein quartic in genus 3, because then 2G plus 1 is 7, and we know that in PSL2 is 7, you have automorphism group of order 7. So I don't want you to focus too much here, but then we say, okay, if the Hurwitz bound holds, we know what happens. So we have to understand what happens when the Hurwitz bound does not hold anymore. So if you have more than 84G minus 1 automorphisms, actually we could prove some things which are rather technical, but then it was a particular subfamily of the curves, which was the candidate. And then we were in the fourth case of the orbit behavior. So one orbit which is tame, the other which is non-tame. And that complicated things a lot, because even if we could prove that we had at least something around G-square automorphisms, this led us nowhere. We needed some different technique, some different things, some different facts. And the key result here, which was really nice, is that is the following. When the automorphism group is too big, then the automorphism had to be a finite simple group. So for a while, I thought, well, I may use the classification. I knew that the group, what I had to be a maximal group. So I went through the classification of finite simple groups, see the classification of maximal subgroups, and then say, this cannot be, this cannot be, this cannot be, this cannot be. But then fortunately for me, well, too late maybe, we stepped on this wonderful result by daubing, which tells you that if you have a non-abelian finite simple group and an abelian subgroup of this group G, if G is not PSL2Q, then the size of the abelian group to the cube is smaller than G, than the size of G. So you say, well, I could exclude by group theoretical argument this case. So you say, okay, Ben, but what's the point? What's the deal here? Well, the deal here is, here I have an automorphism group of order 2G+1, which is cyclic, hence it is abelian. So I could prove that actually the size of the automorphism group was bigger than this guy through this result to the cube. This is bigger than 8G to the cube. And I could use we could use Hence classifications. So we had just to exclude the two hyperelliptic case, but then by hypothesis, the curve is not hyperelliptic. The Suzuki curve cannot be, because the Suzuki group is the only group, finite simple group, whose size is not divided by 3. And well, what was left? Hermitian curve. But the Hermitian curve has possible candidates for the automorphism group, and that was the end of the story. So yeah, so just a quick just want to mention the G+1 case. So we proved something analogous. For the smallest genus of a G+1 curve, which is in this case is genus 4, you may have more than simply G+1 group times its normalizer. And in this case, you have, this curve has 120 automorphisms, and this is the famous Brings curve. This is which attains the maximum number of automorphism group in characteristic 0 for a curve of genus 4. So this is the only exception. In the other case, the group of order G+1 is trivial, is normal, and then you just have its normalizer. But then in this case, we needed a different technique. And actually we use, this is the full classification of the possibilities of the automorphism groups of a curve of even genus in characteristic different than 2. So either you have solvable groups of odd order, either you have a normal subgroup of odd order normalized by the seal of 2 subgroup, or, well, some linear or at most semi-linear groups, well, modulo the odd core of small dimension. We have the Mathieu group here, which gives a really nice curve in characteristic 3 of genus 26, and then some other possibilities. So, but you see here, working with this classification, well, it's of course stricter than having, it's better than having no information on the groups, but I would highlight that it's highly non-trivial to deal with them. You have to know a lot of the structure of the groups, you have to deal with a number of subcases, so it's really, it's rather technical, but it's quite difficult to deal with. So, well, here I will skip this part, and then I will just to mention a little bit what happens for this wild case of G+1 curves. Here again, just to say that these can be examples. So in this case, the characteristic is G+1. The curve has to be trigonal. In this case, it's non-hyperelliptic. And in general, the group just fixes one point. But we have this exception where you have another example of a curve with around g to the cube automorphisms. So one of the things I really would like to see is how many curves, families of curves do we have with more than just g cube automorphisms. So I would like to see that 8 taken down. There might be a lot of possibilities still, but yeah, so this is something we'll be really interested in seeing solved. So well, that's all for today. Thank you very much for your kind attention.
Let's thank Pietro. Are there any questions or comments for Pietro?
I guess I have a question. What is the relationship? I mean, I don't know if this is fair, but what is the relationship between, for example, the class of hyperelliptic curves with many automorphisms and those that have non-classical linear series? Is there some kind of bridge between these things?
Well, hyperelliptic curves, well, at least if the characteristic is bigger than 2, always have the classical linear series.
Oh, I see.
So yeah.
I see.
In the general case, the tendency of curves with many automorphisms is being non-classical. But then sometimes you don't know if they're non-classical or not. One of the first questions my advisor asked me during my PhD was if the Artin-Mumford curve was classical or not with respect to the gap sequence. To this day, I don't know the answer. So yeah, but usually you expect non-classical curves since they usually have many points. You expect to have many automorphisms. But yeah, it's a fair question. So. But still, I'm not. For instance, one thing which I don't know if it exists, it would be nice to prove. Do you have a non-classical curve with no automorphisms?
With no automorphisms.
With no automorphism. Yeah, that would be.
I see.
There is actually a thing, well, not so famous, but pretty famous example in 1956. It's a very nice article, about 7 pages long. A curve with no automorphisms, and you have the equation of this curve. So one may ask if in some characteristic it has, because of course, if the characteristic is big enough, more than 2g minus 2, then all curves have the classical gap sequence. But okay. In the small characteristic case, that might happen. So, for instance, I don't know. For instance, a maximal curve with no automorphism groups, which is another thing I would like to see. There is no reason why it shouldn't exist, not yet.
Thanks.
You're welcome. Thank you for the question.
More questions? Okay, so let's thank Pietro again.
Thank you.